Precalculus, Module 7, Investigation 1, Angle Measure. Number 1A, what is an angle? So if you look in your online textbook, you'll find angle. An angle consists of two rays with a common endpoint. The shared endpoint of an angle is referred to as the vertex of an angle. And here's another pretty good picture from your book. Here's the initial ray of the angle and the terminal ray of the angle. We measure the angle alpha with maybe degrees or radians, and here's our vertex. What does it mean to measure an angle? Essentially, to measure an angle is to quantify the fraction of a circle's circumference that would be subtended by that angle. And subtend means to be opposite to and extend from one side to the other. Essentially, it's like this. Let's say that we have an angle represented by these two rays here. Now, if I put the center of this circle at the vertex of the angle, then there's this fraction of the circumference that is subtended by the angle. It's opposite, let's see, to be opposite to and extend from one side to the other. And this is the subtended piece. And if we find the fraction of this piece in proportion to the whole circumference, then we'll be able to measure the angle. So we should really alter this definition. To measure an angle is to quantify the fraction of a circle's circumference that would be subtended by that angle, but it's only when the circle center is at the vertex of that angle. So what does it mean for two angles to have the same measure? Well, two angles have the same measure if the same fraction of... What does it mean for two angles to have the same measure? Two angles have the same measure if the angles cut off the same fraction of any circle circumference centered at the vertex of that angle. Notice that I could have drawn any size circle over here. As long as we put the vertex of the angle at the center of the circle, then the fraction of this piece of the circumference divided by the whole circumference will be equal to the fraction of this circumference divided by the whole circumference. A chef at a local Italian restaurant wants to design a pizza cutter that will cut his 11-inch diameter circular pizza into 9 equal pieces. He has no access to a protractor, but he has access to a piece of string and a ruler. How might he design such a pizza cutter? So I find this chef pretty strange, and he has a pretty strange idea to make a pretty strange pizza cutter. It's not like the pizza cutters we're thinking of. It makes no sense of like how he would design this like normal pizza cutter just to cut 9 equal pieces. He must have some sort of cutter that he plops down on top of the pizza that cuts all the pieces at once. So if he does have such a idea, then essentially he wants to make a metal apparatus like this one where the pieces are equal, unlike this one where the pieces would be non-equal. So if he gets his string, he can perhaps so we assume he starts and he has sense enough to make his pizza cutter the same size as his pizza with an 11-inch diameter. Now all he has is a string and a ruler, so imagine that if he took his string and just wrapped it around the pizza, maybe around his cutter like so. Just imagine I'm unwinding my string just around this pizza. Essentially, we just take our string and wrap it around the whole pizza. And then we can unravel the string. We can use our ruler to measure the total length let's call the total length L. Then we'll take the total length and divide it by 9, and then that will tell us the distance we would need to mark on our string. We could use a different kind of color here, maybe black, and just mark it so that there's each of these intervals is equal to the length L over 9. Then when we again wrap that string around our pizza, or the pizza, it should have all these markings where, let's see, like a marking here and then one over here, and they should be equal, dividing up the circumference of the pizza equally, and then from the center he can lay his blades down so that they come up to each of these marks, and in such a manner he could create his perfect pizza cutter. The choice of a unit of measure, feet, degrees, pounds, is decided on by some group of people. Imagine that the town council of Leadville decided to measure an angle in a unit called gips instead of degrees. A gip is an angle that, when constructed, subtends or cuts off an arc length that is 1/17 of a circle circumference. So 17 gips will rotate a circle circumference. Using the available supplies, a ruler, compass, piece of string, construct a protractor below to measure any angle in gips. Explain your approach to constructing your protractor and why it works. Recall that the circumference of a circle C is determined by C equals 2 pi r, where r is the radius of the circle, measured in the same units as the circumference. So the purpose of the compass would be to create a circle. Then a protractor looks something like this, where you start with 0 degrees here. Let's see, 90 degrees is up here. Then there's these little tick marks, 1 degree, 2 degree, 3 degrees, etc. So we want to make something like that. So what we could do is to use this circle and get our string, and we want 17 gips to be the circle circumference. So we could take our string, measure, or just rotate it around the circle. Cut the string off at this point, then stretch it out, measure the length, divide the length by 17, and then that will tell you how we need to divide up this piece of string. So if this is x, L over 17, then we just need a distance x from here to here, mark the string, then another distance x from here to here, mark the string, so that we'll have the string divided into 17 pieces. So I didn't count those, but then we can make our protractor. If this is 0, we should really start our string here and go around. Then we'll see that here's like this angle from here to here would be a gip, and then from here to here would be 2 gips, 3 gips, 4 gips, etc. Describe what it means for an angle to have a measure of 1 degree. So let's imagine that we have a circle. Let's imagine that we take that circle and we examine its circumference, and we divide its circumference by 360. A degree corresponds to the length of a circumference that is 1 over 360, 1/360th of the circumference. That will be the length of the arc subtended by the angle. Just like a GIP was 1/17, the 1 degree angle is 1/360th. And when I say 1/360th, I mean that the angle subtends and 1/360th of the circumference, meaning that it's to be opposite to the circumference. So if there's 1 degree here, then this part of the circumference, it's 1/360th of the entire circumference. Same sort of thing for these other ones. 10 degrees, the angle subtends 10/360ths of any circle circumference that is centered at the vertex of the angle. For 47 degrees, the angle subtends 47/360ths of any circle circumference that is centered at the vertex of the angle. So if this is 47 degrees, then this arc length is 47/360ths of the entire circle's circumference, whatever circumference that may be for any size circle. 5. Describe an approach you might use to create a protractor to measure angles in degrees. So first, decide on the size of your protractor, and it should correspond to the diameter of a particular circle. Then use a string to find the circumference of the circle. Take the string and divide it into 360 equal parts. You'd first have to, of course, find the total length of the string, divide that by 360, then mark the string, and then use these two marks to mark the protractor. Okay, now I was told in my instructor notes that this app might be useful. Let's see what we have here. AD is 3 feet, so there's the radius of our circle. Could imagine this top half like you're going to take maybe a piece of plastic and make your piece of plastic the same shape as that top half of your circle, the semicircle. See what else we have. Arc length AB is 4.79 feet, meaning if like the length here is 4.79 feet, so if we took a string and put it there, then stretched out the string and made it straight, we would measure the arc length to be 4.79 feet. The circumference is 18.85 feet, so all the way around. Notice that as I drag this, the circumference doesn't change, only the arc length does. And we have the measure of our angle. And here we have the length of AB, this arc length, divided by the diameter, or sorry, not the diameter, the radius. And that tells you the measure of the angle in radians. So I'm not exactly sure how this is supposed to help us with a the protractor problem, but you see here 1 degree. Pretty small. It's if we took the whole circumference and divided it by 1/360, or divided it by 360, we'd yeah, that's the angle. What else can we do with this? We can move this. Oh, we can change the size of our circle. Notice that the angle doesn't change if I change the size of the circle. It's kind of neat. Okay. Use a piece of string and a compass to complete the following task. Use your compass to construct a circle that has a radius equal to the length of your piece of string. So, assuming I have a piece of string, which I do not, I can lay out my piece of string here. Next, I need to use my compass, which I also don't have, to create a circle such that the radius of the circle is equal to the length of the string. Alright. Construct an angle whose vertex is at the center of your circle, and that cuts off an arc that has the length of your piece of string 1 radius length. Compare the openness of your angle with that of your classmates. What do you notice? Well, if I imagine picking up this string and then taking it and laying it here so that we made an angle, we should notice that about everybody's openness would be the same. There's 1, here's 2, 3. We should have almost 3. If we take that radius and we put it along the circumference, we should go around almost 3 times, because the circumference of a circle is equal to 2 pi radians. So that means half of a circumference is equal to pi radians. And remember that pi is 3.14 something or other. So 3 of these, with a little bit more, will go halfway around the circle. Use your piece of string to create an angle that cuts off an arc that measures 2.5 radius lengths. So 2.5 would be somewhere about right here. Using your piece of string or the radius length as a unit of measurement, how many radius lengths rotate along the circumference of your circle? Compare your answers with those of your classmates. What do you notice? If you go all the way around, you should have 6.28 of these radii, and that's equal to 2 pi. A radian is a unit of angle measure where 1 radian corresponds to an angle that cuts off or subtends an arc length equal to the radius of the corresponding circle centered at the vertex of the angle. Why is the radian a convenient unit for measuring angles? I think maybe it's better if you guys just think about why it might be convenient. Make sure that you understand what a radian is. Describe what it means for an angle to have the following angle measures and represent these angles on the given circle. So if an angle measures 1 radian, then let's see, here's a length of a radius here from the center to the edge of the circle. If we find that length and then measure the same length here, this length here is equal to the radius, then this angle is equal to 1 radian. So the arc length subtended by this angle has a length of 1 radius. The book uses some other weird language. They just note that this 1 radian is 1 over, or it subtends the length with its 1 over 2 pi. If we take our whole circumference and divide it by 2 pi, then we get a radian. So 2 radians, that just means that the arc length subtended by the angle has a length of 2 radii. So on our circle, I would just measure out, here's one radii and then another one, so that my angle would have these initial and terminal vertices and be something like this. That would be 2 radians. And then these are similar. It might be important to note that that last angle pi, since the whole circumference is 2 pi, then pi is just halfway around. There's pi radians, or 180 degrees. If the measure of an angle is 1 radian, approximately what portion of the circle's circumference is cut off by the angle's ray? So remember, the circumference is 2 times pi times the radius length. So 1 radian would be, if we took the distance r around the circumference length, and what portion is that of the entire circumference? Well, the entire circumference is 2 pi r, so it's 1 out of 2 pi. What is the radian measure of an angle that cuts off the entire circumference of a circle? So if you go the entire circumference of a circle, the radian measure has to be 2 pi radians. That's just by definition, because we know that the whole circumference is 2 times pi times r, and the radian measure is just how many radii will go into the whole angle, and that's 2 pi. Number 10, what is the angle measure in degrees of an angle that cuts off the entire circumference of a circle? So in degrees, that's 360. If an angle has a measure of 70 degrees, what percentage of the entire circle's circumference does that angle cut off? So you could just say 70 divided by 360, which is 0.1944 or 19.44%. If an angle cuts off 19.44% of the entire circle's circumference, what is the measure of that angle in radians? So here we know that the entire circle circumference is 2 pi r. That means there's 2 pi radians that make up the, if we find the angle that cuts off the entire circle circumference. So we just need 2 pi times 19.44%, which is about 1.221. So that's 1.221 radians. So if an angle has a measure of 70 degrees, what is the radian measure of that angle? Well, it must be the same, 1.221 radians, since they both cut off 19.44% of the angle circumference. So if an angle has a measure of 1.5 radians, what percentage of the entire circle's circumference does that angle cut off? Well, that would be 1.5 divided by 2 pi. Which is 23.87 degrees. I'm sorry, 23.87%. So if an angle cuts off 23.87% of the entire circle's circumference, what is the measure of the angle in degrees, well, if you take 360 degrees, multiply it by 23.87%, you should get about 85.9 degrees. So if an angle has a measure of 1.5 radians, then it will be 85.9 degrees. Convert the following angle measures given in radians to measures in degrees. So if we have 2 pi radians, we know that well, this one is easy. We know 2 pi radians is 360 degrees. Now if we had 2.7 radians, we use the fact that we already know that for every 2 pi radians there's 360 degrees. Notice this is equal to 1 because these are equal. The radians will cancel out and we'll just be left with degrees here, which is 154.7 degrees. We can do the same thing for each of these. Just take 4 radians, multiply by 360 over 2 pi. So that's 229.2 degrees. Take pi over 2 radians, multiply by 360 over 2 pi radians, and we'll get 360 over 4, which will be 90 degrees. Define a function f to convert the measure of any angle in radians to a measure in degrees. So if you have theta is the measure of the angle in radians, then you want your degrees. Well, f of theta would just be theta times 360 degrees over 2 pi. Now convert the following angle measures given in degrees to measures in radians. Just can do it sort of the opposite way. Put 360 degrees on the bottom so the degrees cancel out, and 2 pi radians on the top. We get 0.908 radians. We have 90 degrees, that'll be pi over 2 radians. We've solved that above. 243 degrees. Put 360 degrees here, 2 pi radians here. Multiply those together and we get 4.241 radians. Define a function h to convert the measure of any angle in degrees to a measure in radians. So if d is the measure in degrees, then h of d would equal d times 2 pi over 360. Now how are the functions related, h and f? Well, watch what happens if you take a composition. This would be f of theta times 2 pi over 360. Which would be theta times 360 over 2 pi. times 2 pi over 360. Notice that you just wind up with theta. So we have inverse functions. We could check the composition the other way and figure out that we just get d to come out on the end.